Okay, no questions. Who else joined? Only 2 of you joined. What's happening to the rest of the team? I hope there is no band or any festival or something like that. Okay, I will share my PowerPoint now. Can you guys hear me? Can JNTU and JNTU Kakinada hear me? Once you confirm, then we can proceed. Okay, JNTU Kakinada can hear me. What about JNTU? Okay, once JNTU confirms, then we can proceed. Did we lose the... Okay, we got Aditya also now. JNTV, can you hear me? Can you put it in the chat? Okay, excellent. Okay, that's good. I see nice, clear videos. 1, 2, 3, a lot of students there. That's good. Let me check. Okay. Let's start with a quote. I like this quote quite a lot. So, because a lot of times they think that success, failures are stepping stones towards success and things like that. They are, provided you use failure as an opportunity, right, to start again more intelligently. If you continue to make the same mistakes over and over again, one can never succeed, right? So the idea is to learn from failures, apply those lessons, and then you keep moving forward towards your goal. Having said that, so what are we going to do today, right? So we started off, or rather we ended the class last week with a 1-minute introduction to balanced search trees. Okay? So according to your syllabus, I'm just supposed to give you some concepts of this and move on without really getting into too many details. Okay? So I'll give you a quick overview of balanced search trees today. And then we will go to the last unit, Unit 6, which is on graphs. Okay? So that is the plan. I don't have any exercise for you today. I thought let me finish this. And when we come to the next module, we'll figure out if there's a scope for any exercise. I did not plan any structured exercise yet. As we go along, if I think of, hey, this is a good exercise thing, I will do it, okay? Nothing planned. I don't know whether you're saying, thank God today we don't have to do anything, or you say, oh my God, we are missing it, right? Either way, we'll figure it out. Okay. So what is a balanced tree, right? I kind of gave you a justification why we need this, right? But we'll go over it one more time. So first of all, a balanced search tree is one where the branches from the root have almost the same height. We are not saying they should all have the same height. We are saying almost the same height. Somebody came online. Can you mute yourself? DMS, I'm muting you. Good morning. Yeah, you still have the... I don't have it. Okay. I muted DMS. I'm muting Aditya. Okay. Okay, I just muted. Should be clear now. So here is a balanced search tree, one where branches of the root have almost the same height. Okay? That's what we mean by balanced. So why do we need the balance? Because if the balance is not there, then the search time becomes order of n, right? So it's kind of like, it's almost like boils down to list, right? This one, if you see unbalanced tree on the right here, 50 is the root node, 78 is somewhere here all the way down. 1, 2, 3, 4, 5, 6, 7 edges. So the depth is 7, right? It's almost like searching a list to search for an item, right? So it becomes order of n. Whereas if you look at the tree on the left, since we have these properties where they are arranged in a way where they are sorted, right? And the search time will always be the log of h. Okay? So log of h is always less than order of n, or, right? In this case, whatever that h is. Okay? So that's why we need the keep the balance. Okay? If you don't keep the balance, then the tree essentially becomes a list, and we have all learned that list, everything about list is order of n. So here is another example where you got a binary search tree of maximum height. Actually, that's a very interesting question. Okay? I can just give you the numbers like that without even showing you the tree. In exam, I don't know if your exams have such questions. I can give a set of numbers, like just like in this figure. I can ask you to draw a binary search tree of maximum height. Okay? And same thing I can say, I draw a binary search tree of minimum height for a given set of nodes. Okay? I say binary, but that means 2. Attending subline is 2, right? So you should be able to draw something like this. Actually, I could have given that as an exercise. I didn't think about it. Okay? So here is one example of a balanced binary search tree called ABL tree. Okay? ABL is actually not really, it stands for the name of the people, the first names of the people who have given this type of a tree structure, and that's why the tree is named as ABL. Okay? There are 3 distinct authors who have come up with this tree structure. Okay? And the good thing about this ABL tree is it maintains the height balance. Okay? And the property to reflect that is, for each node, the difference in height of its 2 subtrees is in the range of -1 to 1. So what does it mean, right? -1 to 1. Basically, there's a one level difference at most, right? Maximum. If you look at the 70, and there are 2 subtrees at the root of 70, right? One which is anchored by 60, and one which is anchored by 90. Correct? Now, if you look at one anchored by 60, what is the depth of that? The depth is, even if you take from the top also, If you go left side, the depth is 2, counting the edges, right? If you go right side, the depth is 3, counting the edges, right? So the difference between left and right here are 1. So in a case of AVL tree, when you do the comparison of the left subtree or right subtree, the difference of depth should be no more than 1. Okay? And the property holds for all the subtrees. If you anchor at 70, you see that property holds. If you go to the next level, you anchor at 60 and 90, that property holds. Right? So if you anchor even at 50, 78, and 95, that property holds. Okay? Then there are other types of balanced trees. Okay? Quite honestly, even I don't know all the types of balanced trees. There are so many different types of balanced trees. Okay? But traditionally in literature, when we're teaching this course, this is another type of tree that they talk about called a multi-way tree. Okay? So what is a multi-way tree? Multi-way tree node has at most 4 children. Okay? And it can hold up to 3 values. Okay? And then it can be perfectly balanced also. Okay? Now again, I realize this is all theory for you right now, right? You just need to know the concept, what the balanced tree is, and see some examples. How you build the tree, how you insert nodes, how do you delete nodes, what happens in the case, how do you maintain the balance, all those things are legitimate questions, right? We'll not get into the depth of that. Okay? Here is some other type of tree called red-black tree. Okay? So what is a red-black tree? It is nothing but a binary version of a 2, 3, 4 node. Okay? So they use some color called black or red. That's why they are called red-black trees. Okay? And then they maintain this height. Anyway, you have this black, it maintains a height, and they'll ensure that the balance is maintained between both sides of the tree. Okay? And then we get into a tree, which is a very interesting data structure, which I actually go very deep into it in my advanced class, called B trees. Okay? So what is a B tree? It's a multi-way tree where each node has at most m children. Okay? So the node itself can hold up to m-1 values. Why you have a node m-1 values compared to m? The reason is you compare the value. Remember, it's a search tree, right? You compare the key and go in the left, right, right? In this case, you can go multiple ways. That's why it's a multi-way tree, right? So if you have 4 children, to navigate the 4 children, you need 3 values. Okay? Less than value 1, greater than value 1, and less than value 2, right? Greater than value 2 and less than value 3, and greater than value 3. So if you look at that one, you will always get m-1 values for m children. And I say it's a more generalized version of 2, 3, 4 tree. Now where you see this one is in the classic operating systems files, like file system is part of operating system, and you also look at databases. When you take a course on databases, your instructor should actually go through B trees. That shows how the data is organized. Okay? It is a very it's a very elegant way of storing the data on hard drives. Okay? So I'll go into a little bit of detail on AVL trees, and then we'll conclude this chapter. So as you can see here, AVL trees, those are the Russian mathematicians, Adelson, Velsky, and Landis. Okay, that's how the name of AVL tree came. Okay, so two conditions. One is the height of the left and right subtrees of the root differ by at most 1. And then the left and right subtrees are AVL trees themselves. That means recursively, all the subtrees also are AVL trees. So you cannot stop with just this one definition, one bullet one. When you are asked to define AVL tree, you have to give both the values here. So which of them are AVL trees here? Let's number them one on the left, 4 on the right. Okay, you can put it in the chat. Which of these are AVL trees? Take 2 minutes. There you go. First exercise of the day, right? The one on the left we call it 1. One on the right we call it 4. So 1, 2, 3, 4. Which of these things are AVL trees based on the property? Take 2 minutes and put it in the chat for me. Let's do a group exercise here. Is 1 an AVL tree, yes or no? Somebody put the answer in the chat, okay? So, Jntuk Kakinada put it, okay. I'm going 1, 2, 3, 4, right? Is 1 an AVL tree? Jntuk Kakinada, you're welcome to put it in for everyone, okay? Is 1 an AVL tree? Yes or no? Okay, let me ask DMS. I'm seeing a bunch of students in DMS in the video clearly. DMS. Somebody from DMS, I want you to put it in the chat today, okay? Is 1 an AVL tree? 1 meaning the figure on the left. When you're looking at the screen, the one on the left, so the 2 nodes. Is 1 an AVL tree or not? Yes or no? Put that in the chat. It shouldn't take more time than that. And the definition is right above the node. We just have to say yes or no. All it is it's a 50% chance you can get it right by answering, right? It's a binary answer. It will take that much time? Maybe I was too fast in explaining, maybe. Maybe the fault is mine, okay? So what are we doing, whether it's an AVL tree or not? First we are seeing height of the left and right subtrees of the root differ by at most 1. What is the height of the left subtree in the first figure? Is there a left subtree in figure 1? There is no left right, there is no left branch. That means the height is 0. Okay? Now what is the height of the right subtree? 1 edge means 1, right? Height is 1. So what is the difference between 1 and 0? 1. That means it is an AVL tree. Got it? You just have to go back to the definition. You have to say, okay, what is the height of the left subtree? That's a legitimate question actually in an exam, right? I can say, what is the height? There is no left subtree. There is no node being shown there. Height is by edges. There are no edges. That means 0. Right? There is nothing to memorize there, right? As long as you know how you determine the height, remember height, equate the height to levels, number of edges. Okay, there are 0 number of edges on the left side. And on the right side there is 1 edge. Difference is 1. So it's a AVL tree. And second bullet is trivial in that case, right? Okay. Now let me pick on. I'm not in Jntuk because I've answered, but they put in private. How about Jntuk? I saw their video too. The second one an AVL tree. Second one from the left. Is that an AVL tree? Yes or no? Aditya, be prepared. Next, you are in line. Can you turn on your video, Aditya Engineering College? Okay. Jane, okay. Okay, Jntuk Kakinada answering. Jntuk Kakinada is very eager. Okay, I asked JNTUV specifically and they answered to everyone no. Okay, Jntuk Kakinada already gave the answer. Okay. Okay, Jntuk Kakinada, stay away from the keyboard for 30 seconds. Okay. Third one. I'll go back to JNTU. I'll go to Aditya. Aditya, I don't see anyone. Can you turn on your video? Unless you don't have any students there. I'll go to JNTUV because I'm seeing their picture. JNTUV, is third one an AVL tree? Third one is this one. Is it an AVL tree or not? Yes or no? The question is to JNTUV. DMS, you can also answer that. The question is open to both DMS and JNTUV now. Is third one an AVL tree or not? Apply the concept that I told you when I was explaining the first one. Start at the root node, look at the subtrees, right? How many subtrees are there? If you start at the root node, at the top level it is at two subtrees, right? I see all of you are in deep think mode or a deep freeze mode, meaning the brain froze. Either that or you are in a nirvana state. What is third one? Is it? See, if you had to show me that at least you are thinking, you can simply answer yes or no and hope for the best, right? Because it's a 50-50 chance. That way you don't look bad by answering. By not answering, you look bad. Okay, keep thinking. I'll move on. I'm not going to answer. I'll let you decide. Okay? Jntuk Kakinada, good job. You answered it correctly, but I won't reveal the answer. Let them figure it out. Okay, here is another valid AVL tree. Okay, and it's important to note that it's not a requirement that all the leaves be on the same or adjacent level, because that is not the condition stated in the 2 bullet points that I gave you, right? They don't have to be adjacent, and it's not a requirement that all the leaves should be on the same level. There are a couple of other concepts. I didn't remove the slide, but I just left them in there just to show some mathematical oriented difference or the properties of AVL trees. Okay, nothing much to explain on this slide. I should have removed that actually. But what it basically shows is if you have different heights of the two subtrees, right? What is the difference between the two subtrees is what it is trying to show. You can ignore this slide quite honestly. Okay. Now, what is interesting about AVL trees is the following. Okay. yes, we know the definition. Given a tree, we can determine whether it's an AVL tree or not. Okay. Now comes the interesting part, right? When you have to insert a node into the tree. Okay. In the binary tree, we have already looked at how to insert and delete, right? I even showed you code examples how to insert a node and how to delete a node. Okay, and still maintain the properties. So in the process of inserting and deleting, you still want to maintain the AVL properties. There's a concept that we need to use called rotation of a node, right? Because at every step of the way, you want to maintain the difference between the two subtree sites is 1, right? At most 1. Okay. So you have this concept called right rotate and left rotate of a node, which is used to maintain the property of an AVL tree as you are inserting and deleting. So what does rotation mean? If you look at the left picture here, right? Right now B seems to be the root of the tree, correct? Okay. Now when you right rotate B, what it basically means is, what it basically means is A is moving up. Right rotate is clockwise, right? A is moving up, B is going down. Down in a binary tree, where would it go? It goes to the right subtree, right? Is it left or right? Since you're rotating right, you're going to the right branch. So you can see how A became the root here and B became its child. Correct? Now, but in the process of doing that, since it's a binary tree, right? What was the child of B? B's child was Y. So everything has to shift, right? So if everything shifts, then you can see B went there, B has a child Y. However, notice one thing, what happened to this beta, right? Alpha, beta, the child of A. What happened to the child of A? Child of A then became the child of B. Because beta or beta, as you call it here, cannot be the child of A here, because then it becomes a three-way tree. You have to maintain the binary tree property. Okay? So in the rotational shift that happened here, you can see how the nodes have moved and the tree is still balanced. Okay? The trick is we use this property of rotation to ensure that the balance is still maintained as you are inserting the nodes. Okay? Writing C code to do these things is a fairly complicated task. Okay? We are not getting into the writing of the code part here, but just want you to know the concept there. So you have the concept of rotation. Now the mirror image of right rotate is the left rotate, meaning now you're rotating left. That means A goes left, A becomes down, B goes up, right? And then everything else based on what I just told you. Okay? Because when B goes up, A becomes a child. You cannot have beta and Y also children of B, because then it becomes a three-way tree. Then one of these things has to go to its subtree. That's how the beta ends up as child of A. Okay. So here are 4 cases when you're inserting something into the subtree of A there. Okay. Inserting in the left subtree of the left child of A. Okay. Right? So you have the left subtree of the left child of A. So inserting left of B. Inserting into the right subtree of the left child of A. So you have beta, you can insert here, second one. See this one, 1 and 2, the way they are numbered here. Okay. Different combinations, right? Then the mirror image of those two, right? Inserting in the left subtree of the right child of A, and then inserting into the right subtree of the right child of A. Okay. There are 4 cases of insertion. Okay. Now, whenever you need to insert something, rotation is required. Okay. So you can see what kind of rotations that need to be done. Again, I don't think I need to get into that level of detail here, but it is there for you to convince yourself, these are the main cases, right? So you need in the case of case 1, what is case 1? If you go back here, case 1 is inserting in the left subtree of the left child of A, okay? Going all the way to the left. So you need one rotation there to balance. Okay? In the other two cases, you require double rotations. And it's hard to remember these things, right? Unless you do it, you would not know it, right? So, but hopefully you will not get those kinds of questions. But the concept that I want you to take away from this is, balancing a tree as you're inserting and deleting is a complex task. It requires this thing called rotation. And these two pictures show that simple rotation for you. Okay. Now I gave some algorithm there. Again, I will not go into the algorithm. You can figure it out. Okay. But there's some interesting exercise here. For example, it says what insertion value would cause a case 1 rotation? So case 2, case 3, case 4. So what I suggest is you take this example that I'm showing you here. Once I post the slides, take this as a take-home exercise, okay? So study these cases here, review these cases here, what I told you, right? Insertion. That slide, okay? And then this slide. Take these 3 slides as the basis to do this exercise. Okay? And then after you do the exercise, if you have any questions, post it in the community and one of us will answer that. Same thing, we have deletion. Okay? Whether you insert or delete, you still have to do the rotation. Okay? Now, what are advantages and disadvantages? Advantages, since you are maintaining the balance, in the case of searches, insertion, and deletions, the algorithmic time complexity would be order of log n. Okay? Disadvantages many, right? Complicated implementation. Okay? Because as every time you are inserting a node, you have to run the balance code, right? That's a big problem. Okay? To find a node to balance, you must go back in the tree. That means you need to have a pointer to parent. Otherwise, you have difficulty. Now, if you recall from our earlier discussion, how can we get a pointer to parent? Anyone remembers how we can get a pointer to parent? If somebody remembers that, put it in the chat. They will deserve a movie ticket if they put it in the chat and the answer is right. Remember, I think we talked about threaded binary trees, right? I vaguely recall that in threaded binary trees, the thread can point to the parent. Okay? Go back and review that one. And deletions are complicated by numerous potential rotations. Okay? So the fact that you have this new concept called a rotation to maintain the balance of an AVL tree is what is adding to the complexity. Okay. But once you add the piece of code to do the rotation, then rest of the job becomes easy, right? So the complexity is hidden in the code, but the usage of an AVL tree gives you all the benefits. After you get past that complexity, then you achieve faster response times when you are searching. Okay? Now, that is the reason why programming is not easy, right? There is nothing easy about programming. It's fun, but it's also a type of thing where you as computer science students should determine, hey, is this for me or not for me, you know? It is not for everyone. Let me put it that way. Okay. That concludes chapter 5. Questions, comments? Again, the only way you can become experts in this is doing lots and lots of practice. I hope I've given you a lot of practice in the class. That's only to give you a teaser, like a movie trailer, right? What we have done in terms of exercise are like movie trailers. You have to do the full movie yourself by writing tons and tons of code to become good at this. Okay, I think it's time to take a 5-minute stretch break now before we launch into graphs, okay? Time now is what, 12:30 p.m. for you there, right? 12:32. So we'll come back at 12:37. I'm assuming the time now is 12:32 there, okay? I'll mute myself and you can get up, stretch, jump up and down, run around, do whatever. I am back. Okay, great. I hope you took your stretch break. I see Pragati coming online. Chaitanya. Okay, good. JNTV, hello, Kakinada. Okay, BMS. Okay. So let me share my screen. Okay, last chapter or last unit as per your syllabus, right? So, if you recall, right, we started off with simple arrays and lists, okay? Then we moved to stacks and queues, all that good stuff. And after that, we moved to trees. As we kept going along when we are doing these things, ultimately, what you are getting is a bag of tricks, as I call it. Right? It's like a toolkit, right? That repairman carries lots of tools, right? Screwdrivers, different types of screwdrivers, right? Phillips, flat, all kinds of things, right? Same thing. Our toolkit as computer scientists are these different types of data structures. Okay? Goal always, of course, is to it's all about choosing the right data structure and also the right algorithm, right? And to reduce the time complexity and storage complexity. So this is the last part of that bag of tools, if you will. Okay? Graphs are everywhere, right? Where did graphs theory come from? Right? Math, right? It's a branch of mathematics, actually. Okay? So we make use of graphs all the time in all aspects of computer science, whether it is routing, like networking, right? So it's all over the place. So very important to know. Okay? So the focus of this module then is to first understand what graphs are, some basic concepts. Okay? Conceptually. Now once you have the concept, then how do you represent those graphs in the data structure, right? Because graph is not a primitive data structure. A primitive data structure is what? Like a struct in C, right? So, like arrays, linked lists, those are all the structures that are given to us. We have to implement these abstract concepts into that using those primitive data structures. So we'll see how these things are represented. Okay? So then in the process of doing that, you will learn concepts as adjacency matrix. Okay? Then you have a whole bunch of graph algorithms. So I'll give you some introduction to that. Now when you have a graph, right, you have two types of traversal called breadth first search and depth first search. Even in trees, we kind of use those terms, breadth first and depth first. So we'll revisit those concepts and look at how those things are done. And then the most famous algorithm that every computer scientist should know is Dijkstra's shortest path algorithm. Okay? How many of you have heard about Dijkstra? I'm looking at DMS. Can you raise your hands if you know who Dijkstra is? Okay, nobody knows who Dijkstra is, at least DMS. Okay? I can't see other pictures here. Maybe there are others who know who Dijkstra is. Let me check. JT Kakinada, how many of you have heard about Dijkstra in your other classes? So raise your hands if you know. Okay, I don't see anyone raising the hand. What about JNTV? Have you heard about Dijkstra? Oh, somebody raised their hand? No. Okay, nobody raised their hand. So I will tell you all about Dijkstra shortly. But let me finish the thing here first. And then we'll get into things such as minimum spanning tree, trims algorithm. All these things are very sort of elegant algorithms to optimize searches, to optimize traversals. Okay, so that is what we'll be seeing at. It's a very interesting chapter. For me, actually, in a data structures class, I always look forward to this particular chapter. Even in my advanced data structures class, I look forward to this. We can have a lot of fun with this, right? It'll be more fun if you interact more. Otherwise, it will not be fun, and I'll wrap it up quickly. Okay? The choice is yours, whether you want to make it fun or not fun. Okay. Before I show this one, let me stop sharing. So I want to ask you, what is a graph? Okay. So the question is, what is a graph, right? Okay. I want active participation from the students, and the students are going to be silent spectators. Faculty members can goad them into answering, or faculty members can answer too. What is a graph? Because you have learned enough math. Without math, you would not be in an engineering institution, right? Somewhere along the way, whether in intermediate or your engineering math in first year, you would have learned what a graph is, correct? Explain in layman terms, right? What is a graph to you? The girl in white with a gray dupatta. She is all smiles in the front. So how about, do you know what a graph is? I'm referring to the student in DMS college. I want some answers, otherwise I'm not going to move forward today. Explain in layman terms, what is a graph? We use the word graph as such a common term, right? I hope I'm not asking a stupid question. Okay, let me ask you a question in a different way. Have you ever drawn graphs in your career? People are smiling in DMS. I'm not sharing anything, right? So graphs have nodes, okay? Also called vertices, okay? And then when you have vertices, you need to have what are known as lines or edges, right? Edges connect vertices, okay? So that's the key concept of a graph, nodes and edges, okay? So I'll give you some, I'll go back to the slide in a second, okay? But let's look at some concepts here, okay? Let's say I have a node. I can call it a node, right? Then I can draw another node. I can draw another node, and I can draw another node. Okay. Now let's actually, and then let's say I can draw an edge like that, an edge like that, edge like that, edge like that. These are edges. Okay, now let's say I call this one Kakinada, and I call this one Vijayanagaram. Okay, I don't know where all of your colleges are. If I screw up the names, please bear with me. For lack of my geography knowledge, I'll call it Vizag and maybe one more name. I know this is not part of Kakinada, Jntuk Kakinada, but for the sake of example, I want to call this Hyderabad. I didn't spell it right. Okay. So when you're drawing a graph, right? Think of it. I'm just talking whatever is coming to my mind without going to the slides first, right? So you know that your Jntuk coordinator, like in this case, let's say ASN Garu, Chakravarti Garu. He's the Moocs coordinator, right? So the Vice Chancellor gives him a task. Hey, I want you to go to these institutes, have meetings with them, talk to them in person, understand how Moocs is working for them, gather all the notes and come back and report to me as soon as possible. Okay? So each of your cities where Jntuk Kakinada is, there is a node. Okay? And they are all connected in some way. Okay? And the edges, so the nodes are the institutions and the edges are the routes or routes or distance, whatever you want to call it, the connection point, right? Now, what is the best way for the Moocs coordinator to travel all these places and come back to Kakinada? Right? What is the shortest possible way for the Moocs coordinator to travel to all these places and come back? That is modeled as a graph. Right? So he first has to list down on a piece of paper, oh my God, I have to go to Vijayanagaram, I have to go to Vizag, I have to go to Hyderabad, I have to go to Gudlavalleru, wherever that is, I have to go to ASET, right? Or DMS college, wherever that college is, right? How does he know what is the best way to travel to all these places in either the shortest amount of time or in the cheapest amount of money possible, right? There has to be a way of figuring that out. And thankfully, we have what is known as graph theory to figure that out. Okay? Everything about graphs is a very practical way of looking at the reality around you to solve problems. Okay? That's why we need graphs. Okay? Now, you all have your smartphones, right? I hope no one got the Note 2 or whatever that got burnt in the Air India flight or Jet Airways when they were traveling, Galaxy Note or something, right? But other smartphones. So all the mail and all that you check in your Gmail or Yahoo or wherever you check your mails and all that, when I send something from here to you, all of you in the community, all that, you are getting the messages instantly, right? How is that coming? The Google and all the other mail servers, they're using graph algorithms to route the messages from source to destination in the most optimal fashion. Okay. Now later, when you take networking classes, you learn a lot more about these graphing algorithms because the entire packet routing is based on some protocols which will give the shortest path. Okay. Another classic case, this is hot off the press. I was reading about it, even I didn't know this one, by the way. I read it with a lot of curiosity also. The other day I was reading an article about Amazon. Okay. Have you ordered books or anything from Amazon? In India, do you people use Amazon? By the way, the wonderful girls in the front, what are you people talking about? I see DMS college video clearly, and all of you are engaged in a serious conversation. Let me pause here. Maybe the lecture is disturbing them. Madam, you can check on them as to what they are talking. I'm referring to DMS. You seem to be engaged in some serious discussion there. Should I move on? Or you can go outside the classroom, do your discussion and come back. So DMS people are disturbing the class. That's what I said that. I hope you are able to hear me clearly on that. Okay. So what I was saying. So when you are, I lost my train of thought. Give me a second here. What was I talking to you about? Yeah, Amazon, right? So we use Amazon a lot for ordering and shipments and all that, right? The article was about how Amazon stores the products in their warehouse. Okay? So there are millions and millions of products, right? Okay. Let me ask the DMS. Let me put it in the chat so that way everyone can see it, right? There is no point putting your hand over the mouth. You should not be disturbing a class. Okay? As simple as that. If you're in my class here, physically, I would have given you a timeout. You're not middle class students or teenagers, right? Middle, like, what do you call it? Like grade school level students. You are engineering students, okay? So I don't take this kind of nonsense. I should tell you very clearly. Either you can talk when you're doing an exercise, or you have no business being in the classroom. If you're not interested, get out of the classroom so other sincere students can learn something, okay? So don't repeat that again. Okay, let's move on. So this Amazon thing that I was telling you, right? So the article says, when typically what is the common mentality that we have, right? When we have to store products in a warehouse, we say, okay, these are all computer parts. I'm going to put this in this cubby. These are all printers. I'll put them in another cubby. These are printer cables, I'll put them in one cubby and so on. That is our mindset, right? So we think we are trained to think in structural manner like that, in a very structured, organized way. But the article gave very interesting insights. What it said was, as these parts come into the warehouse, they are put in different cubbies randomly. Okay? Totally against the normal grain of thinking. Now, you would say that, okay, when a customer is ordering a part, would that cause more problem? Because I don't know where the part is, right? Let's say my daughter placed an order for a book. We order like Amazon every day, almost every day, something or other, right? So there is a warehouse clerk. How would he or she know in which cubby that book is? Because there is no structure to the cubbies, right? Or bins, as we call them, bins. Or books go here, electronics go here, nothing like that. Anything can go anywhere in the entire warehouse. So that means it's like a mess, right? If imagine in your house you're storing things in a messy way. Okay, in the case of boys, let's say your trousers are at one place, your shirts are in some other place, like that, and your books are in some other place. You don't know where to search. It is such a big mess, right? But it turns out the way Amazon is doing is a fantastic way to optimize the fact that they can fulfill a customer's order quickly. Because I place orders 10 items, right? By doing it randomly, they are able to find those elements faster. It's very counterintuitive, right? It's not structured, but it's faster. How is that possible? So I said, let me read the article more. So what they do is when they come up with the customer order, the system routes the warehouse guy, hey, go in this order. This is the path that you need to follow in the warehouse. Warehouse is nothing but a bunch of columns and rows, right? It's a big table of shelves, different shelves. Because as these items are placed in the shelves, they are scanned, meaning they have this barcode, right? So the system knows, based on a customer order, what is the shortest route the warehouse guy should take to pick up those items from the shelves and put it in the customer order. Okay. Very interesting concept. Where do they come up with those things? Thanks to the graph theory. Okay. You name any part of life, there is graph theory involved in that. Even the algorithm that you come up with, there is graph theory involved in that. Okay. So that is a justification for understanding these things. Okay. Now let me share the screen here. Give me a second. Where is the share button? Okay. Okay, now more formally. So it's a data structure that consists of a set of nodes and a set of edges that relate the nodes to each other. Okay. So you can see here, like in this case, it's a graph of all the cities. Okay. And there's some way of traversal and some relationship between them. Okay. Mathematically, it's defined like this. It's a set of vertices and edges. Okay. V stands for vertices, and it's a finite non-empty set of vertices. And D are edges. It's a set of edges. Okay. And edges are nothing but, it shows the pair of vertices where that edge connects those. Okay. Now, a couple of more concepts. Okay. When the edges in the graph have no direction, the graph is called undirected. Okay. In this case, we see there are no arrows. Okay. It's an undirected graph, and the vertices here are A, B, C, D. typically shown as circles. Whether I show them as circles or rectangles or square, I wouldn't care less. But typically in graph theory, we show them as circles. Okay? And then when I give you a tuple like E graph, E of graph 1, you can see how I said that, hey, there's a line that goes from A to B, comma A to D, okay, comma B, C, and BD. Okay? So in exam, I can give you the bottom part here, saying these are the vertices, this is the tuple corresponding to the edges. You should be able to draw the picture above. Okay? Sorry. Okay? Now, in contrast to undirected, directed means there is a direction. It means there is an arrow. Okay? Now, when you have a directed graph, that shows in which way it can be traversed. That's what arrow has a meaning, right? Okay? So you can see here, as it says in the warning, if the graph is directed, the order of the vertices in each edge is important. Okay? There is a communication path from 1 to 3 does not automatically imply there is a communication path from 3 to 1. It has to be explicitly stated there. That's what the direction is important. Okay? Now, what's the difference between a tree and a graph? Okay? Trees are nothing but special cases of graphs. Okay? Do trees have cycles? We learned from our data structures class on trees. Trees do not have cycles. Remember, cycle meaning coming back to the same thing. Whereas later you will see graphs can have cycles. Okay? When you have a cycle, starting point and ending point can be the same. Okay? Whereas trees, they do not have cycles. It's a hierarchy. There will be one unique path. Remember, in the case of tree, there's always one unique path from the root to a given node. You'll never see multiple paths. Okay? But it's still a graph. Tree is still a graph. It's a special graph. Okay? Now, some additional terminology. Adjacent nodes. Two nodes are adjacent if they are connected by an edge. Okay? And what is a path? It's a sequence of vertices that connect two nodes in a graph. Okay? It's very similar to tree, right? Now, a complete graph is one in which every vertex is directly connected to every other vertex. Okay? Again, these are definitions. There's nothing to say why, right? Interesting questions you can ask, right? What is the number of edges in a complete directed graph with n vertices? Right? So, directed graph means if you look at this one ABCD, since it's a directed graph, it's a completely directed graph, meaning, so from A to B you have a direct line, from A to C you have a direct line arrow pointing, and from A to D you have a direct line. Similarly for every node. Go to B, from B you draw a directed line to A, C and D, and so on. Okay? So you can see what is the value there. Okay? Same thing, if you have an undirected graph, here, what is the number of edges that you will have? Come up with the formula, which of them, you figure out which of those things is right. Okay? But you can notice one thing, in an undirected graph, you only draw one line. You don't need to draw two lines. Only in the case of directed graph, to draw a completely connected graph, you need to draw two lines. For example, here, say J to N, there's only one line. There's no need to draw another line from N to J, because it's the same line. Because it's not a directed graph, right? Unlike in the previous picture, you can see from A to B you drew an arrow, and from B to A also you have to draw an arrow. Now we have weighted graph. What is a weighted graph? Meaning the edges have values. Okay? So in this case, you can see the values that are listed there. Obviously, these are all cities in US. Okay? And the edge values, if you see 200 from Austin to Dallas, that's 200 miles. The distance from Austin to Dallas is 200 miles. In this case, the meaning of the value is miles. It could be anything. Okay? It could be time, it could be distance, it could be cost. Okay? For example, let us say going from Hyderabad to Delhi, flying from Hyderabad to Delhi can be a cost of $150. But coming from Delhi to Hyderabad maybe $300. The cost is not the same. Whatever cost is going from Hyderabad to Delhi is not the same as cost from Delhi to Hyderabad. It's all supply and demand, right? The costs don't have to be the same. Okay, so that is the weighted graph terminology. Okay. Representing graphs. How do we represent graphs? By the way, think of it as like a high-level overview. We'll get into the details more and more over the next 2 weeks. Okay? Where you'll get to do a lot of exercises too. Okay? So there are two ways we represent graphs. One is called an adjacency matrix, and the other one is called an adjacency list. Okay? So when you have too dense a graph, then you use adjacency matrix, and when the graph is sparse, you use adjacency list. Now, when you say a graph is dense, the number of edges tend to come close to the square of vertices, right? That's how it says there, E close to magnitude of V raised to 2. In the other case, it's less than. Okay. So how do we show that, right? Let's look at some examples here. Okay. So you draw a matrix of size V by V. Okay. V is the number of vertices, remember? Okay. Each row, column J corresponds to distinct vertex J. Okay. 1 in cell means if there exists an edge, otherwise it's 0. Okay. In an undirected graph, 1 in Ij equals to 1 in Ji because it's the same vertex, right? And if we see in Jj, meaning in the cell corresponds to J1, there is a self loop in vertex J. Remember, you can have self loops too. Now all this is theory, right? Let's look at some example here. That way maybe we'll understand it better, right? Okay. So you have, let's take a look at the left one, right? What is this one, by the way? This is the adjacency matrix, right? Used when it is dense. So you have 1, 2, and 3. And it shows here the number of edge count is approaching the number of vertices count, right? So you write 1, 2, 3 on the top, that's the vertices. 1, 2, 3 left side, that's what it says. Draw a V by V table. And then you go from each vertex to rest of the nodes and see if there's an edge. You mark the corresponding cell in that table as 1. So I see an edge from 1 to 1, there is no edge. There is no self loop. There is no edge from 1 to 2, as you can see, that's why it's 0. There is an edge from 1 to 3, that's why you put 1. Okay? Now you go to edge 2, node 2. Node 2 has 2 to 1, there is no edge, there is no line, right? You put 0. 2 to 2, you put 1. Why? Because there is a self loop here. You see the self loop here? This is a self loop, right? So that's why 2 to 2 you have 1. And 2 to 3, is there a direct edge from 2 to 3? No, because there is an edge from 3 to 2. Directed. Remember, that's the difference. So there is no edge from 2 to 3, you put 0. Like that you build a matrix. You'll get to do some exercises along those lines. Okay? So in the case of 1, 2, 3, and 4, you can see clearly how to build the matrix, right? So 4 actually has everything zeros. Now later on, when you are doing your operating systems or compilers class, you will draw what are known as state machines, finite state machines. Those are all graphs in essence. Okay? And when you have an edge when you have a node like a 4, which is not connected to anything, then that 4 should not be part of your solution. So you would learn some concepts like that. But for now, here we are just seeing the graph concept. If I give you a graph like this, I want you to fill out a adjacency matrix. You should know where to put 1 and where to put 0. If there is an edge, you put a 1. If there is no edge connecting those vertices, you put a 0. In the case of a unidirectional graph, which I am showing you on the right, if you have an edge connecting 2 to 1, by default you assume there is an edge connecting from 1 to 2. That's the reason why you see 1 in both the places, 1 to 2 and 2 to 1 also. In the case of a directed edge, direction matters. So if you say an edge from, let's say in this case, 3 to 2, if you go to 3 and 2, you'll see 1. But if you go to 2, from 2 to 3, you see, go 2, from 3, you'll see a 0, because there is no directed edge. Okay? Okay. Now, there are a couple of slides here. I know that it'll be like a bouncer to you to begin with, but I left it there just as my cheat sheet to come back to it later. Okay? We talked about storage complexity when we have this type of things. There's a way of calculating it. It's basically n times n, right? So that's the reason why you get n squared off. In this case, we call it V, because V is the number of vertices, right? And then you have row and column. So you typically need to use the storage of V squared. Okay. I'll skip this for now. We'll come back to some of these things later. Okay. Now, what happens here is most of the graphs, when you're trying to solve problems, they tend to be sparse, meaning you'll have less edges. So when you get an exam question, what is the difference between when do you use adjacency matrix versus when do you use the other one? It boils down to the number of edges compared to the vertices. Okay? When you have dense meaning the number of edges are close to the number of vertices, use the adjacency matrix. But if it is sparse, meaning if it is not close, then you use the other representation. Okay? So what is the other representation? It's called an adjacency list. Okay? It's an array. Okay? Number one, it's an array of size V, number of vertices, right? Each cell holds a list for associated vertex. Okay? So we'll see what that means again, right? Same example. It is showing you, remember it's an array, right? So it is showing you what it says here, an array of size V. Okay? Each cell holds a list for associated vertex. Okay? So you can see here, it's an array of 1, 2, 3 vertices. Okay, 1 is connected to 3, the value. It is just showing the value, right? And 2 is connected to 2, and 3 is connected to 1 and 2. Okay? Takes less space than a full table. That's what it means. Okay? Because when it is a sparse matrix, there is no reason to waste a huge n by n table, right? Because you do not have edges from all the nodes to all the other nodes. Okay? So use a list concept there. Okay? So the storage, instead of becoming V squared, now it has just become number of vertices plus number of edges. Okay? So it's more efficient in the case of sparse connections to use the adjacency list, because you save a lot of time in terms of time as well as storage too, because Less storage required, faster to search, right? More storage required, more time to search. There are a couple of ways of implementing graphs. Okay. One is an array-based implementation. Okay. One-dimension array is used to represent the vertices, that is in the case of sparse. A two-dimensional array, which is nothing but an adjacency matrix, is used to represent all the edges. Okay. So what I will do here, I'll stop right here. Okay. Take this picture that you're seeing there. I want you to draw an adjacency matrix. Practice drawing an adjacency matrix. Okay. So I have Austin, Dallas, Washington. You can see the slide quite clearly, right? So I want you to draw an adjacency matrix for that, not the one-dimensional array. I'm talking about 2D array. Okay. Do it in groups of 2. I showed you a table where I said all the vertices. In the column, you should put all the vertices, and in the rows also, you should put all the vertices. Okay? So, on the top, you should see from left to right. In this case, I'm saying left to right, could be anywhere, right? I would have like Austin, Dallas, Washington, Denver, Atlanta, Houston, Chicago. I'll have 7 columns. I will have 7 rows in the table for each of the cities. Austin, Chicago, Denver, Washington, and so on. Then you fill out the table. If there is an edge corresponding to that, you put a 1. If there is no edge, put a 0. So that's how I want you to fill out the adjacency matrix. Okay, ready, set, go. Take out a piece of paper, draw a table, and put the values. Do you have any questions on the instruction as to what you're supposed to do? Put it in the chat and I'll clarify that. Don't stare at the screen. Start writing on a piece of paper. Do you guys have paper in the classroom or notebook where you can write? And take it out and start writing. Create an adjacency matrix for the picture that I'm showing you. Anyone has questions as to what needs to be done? I'm asking you to draw an adjacency matrix for that. Okay, I do see some students in DMS trying to write. Okay, let me go back to the picture now of the slide. It's a typical high schooler assignment that should be done in 5 minutes or less. Since you are all second-year engineering students, you should take 3 minutes to do it, since you know the definition of an adjacency matrix. So whenever somebody finished it, put it in the chat that you finished, then I can go to the next slide and show you the solution, and we are done for today. By the way, all these concepts we'll be going over the next 2 weeks and more in depth with more practice exercises. This is only a sample lecture on this.
Sir,
Jntuk Kakinada is done. I'll give another 2-3 minutes for other colleges too, and if I get JNTV or any other college saying they are done, then we can move to the next slide. And by the way, the girls who I picked on from DMS, don't feel too bad about it, okay? Because there's an element of, you guys need to have an element of seriousness when you're learning, okay? Your faculty members, myself, we take it seriously. We spend a lot of time and energy to share whatever little knowledge that we have with you. And we expect the same level of responsibility from you too. We are almost coming to 12 p.m. That's 1:30 p.m. rather for you. For me, it's 12 a.m. So let me go to the next slide and see if I have the solution there. So this, if you look at the adjacency matrix on the right, you can see how all the cities are represented, and then corresponding values. Wherever you have an edge, you put the value, and wherever there is no edge, all of them would be filled by zeros. And those are all the cities right on the left. Pretty straightforward actually. There's nothing complex about that. Okay, I think I'll stop here. We'll get into more details next class. Okay. Questions, comments?